Hi everyone. Hi everyone, welcome to CS 109. Welcome to the second lecture on visualization that we have. So the plan for today is that I'm going to start with visualization. It will be about 1 hour, and after that Raphael takes over with explaining some details about the homework. Okay, so last time we talked about the different goals of visualization. So we talked about presentation and communication, which is very different from exploratory and confirmatory analysis. So in communication, it's just about telling something what you already know, and exploratory data analysis is then really finding something that that is new for you. Yeah, we talked about the different data types, so quantitative data, ordinal data, nominal data, then about dimensionality, so we discussed what to use for 1D data, 2D data, 3D data, and the second half was about statistical graph types, and we talked about the different tasks that you could have, so it could be to show a correlation, it could be to show a distribution, it could be to compare something, and so on. Yeah? Okay, today will be quite different. So we are going to talk about what makes a visualization effective and what makes it non-effective. Yeah? And for this, I will start with some really good examples, and after that, we're going to talk about visual attributes. So that's really the basic units, the basic vocabulary for visualization, like color, shape, size, and so on. Then there is a little bit more to tell about the visual attribute color, because it's often overused and used in the wrong way. So I want to clarify that. And the last part will be about design principles. Yeah? And you shouldn't end up doing this banana chart. You should be smarter than that. Okay, so effective visualizations. This is the basic process of visualization. So we take some data, we create a graphical representation, and this process is known as visualization. Yeah? And we have some goal, some question that we want to have answered, and we're using interaction or inspection of this graphical representation to actually find that answer. Yeah? And this interaction could be just a one-time plotting of the graph, or could be more interactive, like with this lineup ranking example that I've shown to you last time. But there's a very important difference between an expressive and an effective visualization. Yeah? A visualization is expressive if it shows the data, just the data, and not more that needs to be there to answer the question. Yeah? So if you have a huge data set, or if you have this tiny Titanic data set, and you have a question that is just related to the age and the fare of the passengers, then you need a chart which obviously only includes these two attributes. Yeah? And this is expressive then. And effective is different. It's effective if it's very clear, if it's well designed for perceptual purposes. Yeah? And we will see some examples. And today will be more about this effective part. Okay, so these are examples that are not effective. And the sources are US Treasury and World Health Organization, so they actually should know better. But they don't, unfortunately. So we have 3D pie charts. We have a really bad use of different colors, 3D bar chart. We have these grouped bar chart where it's very hard to see what's going on. So these are errors that we try to fix today. This is also not effective. And these are figures from Nature papers. Yeah? So that's really the highest standard journal that you could have. Yeah? And obviously, there you see the same problems going on. Okay, there's also a really nice platform. It's called WTF Visualizations. I will put it like this. I was told to not use a different term here. What you see here is a pie chart. It's exploded, which is a bad thing. It has way too many slices. Yeah? It even has this other portion, which is sliced again. It reuses the same colors over and over again, which makes no sense at all. It has a bad labeling, so you have this crossing here of this line, which is also not good. But I guess this example is even worse. So there's a program, a radio program on BBC, and they try to just show the highlights of their playlists. And what you have here, they really have 11 pages of this legend. You can click next, 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 and there you have so many slices that you get this, what we call in computer graphics, moire effect, these artifacts here. And of course, you can't read this. These are some other bad examples. An exploded 3D pie chart, which is like really a sin. Then we have bad labels. We have no labels, but this legend here, and it doesn't sum up to 100%. So it's also really nice. And so if we're talking about pie charts, there's this. So there's a really popular blog in visualization. It's called Eager Eyes. It's written by Robert Kosara, who used to be a professor and then moved to industry. And he's doing visualization at Tableau. And there was this counterpart which popped up on the internet. It's called Eager Pies. And what they're doing is they take reasonably well-designed charts and turn it into nightmare bar charts. So I will just click here. It will bring me to the browser. And they will try to find scientific arguments to why they should introduce something else. And you can read through it. It's very entertaining. So they will start with this. Then they say, OK, we should use more colors. Then they introduce this ring here. Then they say, we want to, we don't need this white space here, so we fill it. Then the labels are bad, so we remove them. Then they explode it, and they also have some arguments for that. They create a 3D version of it. They move the red ring to the front. Then they add this background, and finally, to make it more, even more convincing, they add this animation. So that's really a great example. They take the other way around. They take a good visualization and make it bad. Okay, so another example would be the periodic table of elements. We've all seen it, and I think it's really a good example how you can organize a chart in a meaningful manner. You all know the rows are the periods, the columns are the groups. They're sorted from top to bottom by the atomic number. So it completely makes sense. And we know the structure and we know how to interpret it. But there are really lots of examples where they just took the periodic table structure and used it for something else, where it has no meaning at all, like the periodic table of wood or the periodic table of accounting elements, the periodic table of famous trademarks. If you just put in periodic table on Google, it will give you all different kinds of examples. The periodic table of marketing elements, this is very nice because you have face-to-face, you have, I don't know, coffee here somewhere. Yeah, coffee. Yeah.
Can you make a periodic table a bad periodic table?
Yes. This is actually kind of related because they try to make a periodic table of visualization methods, which is as bad as the previous examples. And Robert Kosara actually wrote visualization is not periodic, period. Because there is no such structure as with the periodic table. So it doesn't make sense to actually fit it inside this structure. So you should, of course, avoid this. And I think this is a really good example to show the difference between effective and non-effective. Well, these are much better. They're very clean. They just show you what you're supposed, what you need to know about the graph. These are also from US Treasury, from World Health Organization, and Nature. So there are, of course, also good examples there. Before we switch to actually how to create these effective visualizations, I want to explain this Bikini chart. Who has seen this before? Okay, only a couple of people. So in theory, this is a really clean visualization. I will not argue there. What it actually gives you is it's a data set by the Bureau of labor statistics, and it shows you the loss of jobs from 2007 to January 2010. Yeah? And there you see the Bush administration, Obama administration. It's also very intuitive because they use the colors that are used for the different parties. So red would be Republican, blue would be Democrats. But there are some very, very interesting design choices. Yeah? And this chart was published by the Obama administration. Yeah? So what they want to achieve is they want to make Obama look better. Yeah? So what they've done is actually the most important design choice is they turned the bars to point downwards. Yeah? So because usually bars point upwards. Yeah? And what it gives you is the visual impression that in the Bush administration everything got worse and then it got better. Yeah? That's our intuitive understanding how to read this. If you would draw it like an actual bar chart, then it would be Bush administration did actually a good job because bars are getting longer, and then it decreased again. So you can completely steer what kind of message you want to convey with your chart. Yeah? I think this is very interesting. So you really need to try, if you see a visualization, try to find out what the purpose of it was, who published it, in order to understand their intentions. And there's also a very interesting design choice here, and it's not that clear on the projection, but the colors, there's a gradient in the colors. So the colors are darker at the end of the bars, yeah? And they're lighter here. And also red is much darker than the blue. Yeah? So blue is a bright blue, it's happy, and red is bad. Yeah? And they use this red to darker red gradient to actually make it look more severe than it is. Yeah? It has the impression of blood. Yeah? That's at least how Robert Kosara interpreted this in his blog. Yeah? So it gives you a really negative impression about the Republicans and a very positive impression about the Democrats. Yeah? Okay, so now let's talk about what exactly makes a visualization effective. Yeah? And there are these visual variables, this basic alphabet or basic vocabulary of visualization. And the guy who actually published a really important book called Semiology of Graphics is Jacques Bertin. So Jacques Bertin was a French cartographer, and in 1967 he published this Semiology of Graphics. And that's really the theoretical principles for visual encodings. Yeah? And he did a really good job. And most of the stuff is still valid, of course, today. So he introduced visual marks. And visual marks are basic geometric elements, yeah? Points, lines, and areas. And when you think of it, every visualization is composed of points, lines, and areas. Yeah? Then we have different ways to alter, to change these visual marks. Yeah? And these are called visual variables or channels. We have position, which is known to be a very, very strong visual variable. We have color. So position we can use in a horizontal direction, in a vertical direction, or in both directions. So if we have a scatter plot, then we use it obviously in both directions. Then we have color. That's intuitive. We have shape, which is not that effective compared to position. We have tilt. That's angle. That would be the one we use in pie charts. Then we have size. That's the length. If you have a bar chart, this would be the length of the bar. We have area. That's also used in a pie chart. We're supposed to interpret areas, and we're not really good at that. And volume. And these are the visual variables that you have. So you choose the visual marks and then assign the visual variables to the marks, and in the end you will get a visual representation out of it. So when we use the marks, when we use length, we get bar charts, for instance. When we use position in both directions, we get a scatter plot. When we add color to it, then it looks like the third one. And we could also change the size. Yeah? So we can add more and more channels, which at some point makes it harder to interpret, of course. Yeah? So this would be an example that Raphael showed last or in the first lecture. So, and my question would be, what visual variables are used? Yeah? Position, area, and color. Yes, exactly. What would be about the vertical position? So the horizontal position is, yeah, the different ranges. What would be the vertical position? Nothing. That's just because to stack it, to not make it overlap, which is also a valid design choice, of course. Okay. When we talk about visual variables, it's important to know how they can be separated, and how many of them you can use at the same time. If we use position and hue, like in a scatter plot where we color the dots to some categorical attribute, then this is fully separable. We can interpret the position and we can interpret the hue, so the color. If we use size and hue and we mix it, then this already influences the other attribute, because smaller dots that have a color, that makes it more difficult for us to interpret them. So this color, these bigger dots, they're visually more salient. And the smaller dots, it actually makes it harder for us to interpret color. So they're not separate anymore. This is worse if we combine width and height. We encode something in the width and in the height, a different parameter or different attribute of our data set. Then what happens is that we separate it into 3 different shapes, and we group these shapes automatically. So this would be one group, the round ones, this would be one group, these horizontal ellipses, and the third one. So there is some significant interference here. And the last one would be where we have major interference is if we use different channels of color. So we have these primary colors of primary channels of color, red, green, and blue. And if we mix them, then we get major interferences. And this is, of course, something that you don't want. So the thing that I want to convey here is that there are some visual attributes which can be combined, and some others, they can't be combined without influencing each other. Okay, so there are so-called pre-attentive features. If you want to make something pop out from your visualization, then you can use these visual channels and create these visual pop-outs. For instance, if we have color, then we just need to change the color to make it pop out. That could be if we let the user select a part of the data and we highlight it in other parts, so in other plots showing the same data, then this would be a very good technique. And pre-attentive means that we don't need to think about it. It's something that can be solved with our perceptual system. We don't need cognition, so we don't need our brain to actually see that this pops out. And that makes it very fast, and that's called a pre-attentive feature. It's still pre-attentive if we add more of these blue dots. It's also pre-attentive if we use shape for it. You can immediately identify this guy here. It even works if we add more elements. You will immediately see, well, this guy is different. It also works for if we mix color and shape, then it takes some time for us to find this guy because it's different. And if we add more and more, so here it doesn't work at all. We really need to search in a serial fashion, which is very, very time consuming. So we have some influences here. The same works not only for color. You can make something pop out by using other visual attributes, like you can change the slope or the angle. You can change the size, you can change the shape, and so on. This works for many different visual attributes. This is also very interesting because there is what we call a feature hierarchy between the visual attributes. So this is pre-attentive for us. So we don't need to think about it to actually separate this part from the other part. The same is true for this one. Yeah, we don't need to think to see the grouping, to see the two different groups on the left and on the right. Here, for color, it also works, and that tells us that color is stronger than shape. Because here, if we just have the shape in the upper part and the color in the lower part, it's much harder for us to actually see this group here. And this is perceptual studies. And that's just some theory that you need to be aware of when you create visualizations. Something that is really important for InfoVis is grouping principles. There is one grouping principle called containment. So if an example that I put here is so-called bubble charts by Collins, and they have a scatter plot and they add this shape around it to make it belong together. And this is a very strong grouping principle. It's called containment. Another grouping principle, so grouping principles are effects that we want to use to make things belong together. Another very strong grouping principle is connection. That's what we use when we show node link diagrams. So in this D3.js example, so D3 is a very popular JavaScript library nowadays to create interactive visualizations on the web. We use connection. Then we also have proximity, which is very strong. If we want to make something belong together, we just move it closer to each other. And this is what we use, for instance, in force-directed graph layouts. So if you have a clustering, then you put the points that cluster together closer to each other. And this is called proximity because they will form these groups then. Then we have similarity. That works with color and also other visual attributes. We just change the color of some points here and they belong together. Even here, if they're part of different scatter plots, like in this case, they belong to the same group. We know they are the same. We know that they are the same. That's a very strong grouping principle. Then we have continuity, which is also really interesting because you can use this visual effect that our brain understands immediately. If something continues, then we will autocomplete it. That's what our brain is used to. For instance, this line and this line, we will immediately see that we have two lines here. And that's used in this New York Times swing state visualization. Because you have these continuous effects and we just used to follow these lines. And that's very natural for us. And there are some more like common fate. It misses the arrows here. So if that's the bird swarm effect. If something moves in the same direction, we will perceive it as the same group. So if the first two dots would move to the left and the other ones would move to the right, we will perceive that naturally as a group. And we have closure. So that's also, I would say, an autocomplete feature of our brain. These visual variables, they can actually be ranked by data type. So Bertin already in 1967, he thought about, we have categorical data, so categorical data is nominal data, we have ordinal data and quantitative data. And we discussed that last time. And then he took a look at how effective the different visual attributes are for these different data types. And something that you really should remember is that position is always the strongest. Independent of the kind of data that you have, position is always the strongest. And then, for instance, color works for categorical data, for nominal data, but it doesn't work for quantitative data. And we will see some examples later on. And then this was refined and refined by Cleveland, McGill, and McKinley later on. And this is a very recent screenshot from Tamara Manzner's book, which came out, or which actually is available this month. It's very new, and it gives a really great overview over InfoVis, I would say. She's a Canadian professor, and she's really well established in our field. I will have it later in the slides in the reading section. So she actually ranks these attributes by their effectiveness. So least effective and most effective. Yeah? At the top we have position. Yeah? Position on the common scale is easier to interpret as than position on an unaligned scale. Yeah? Then we have length, is also very effective. We use it in bar charts. Tilt, area, depth, that would be a 3D position. And then, that's surprising for many, I guess, that color is really not that effective. And here we're talking about ordered attributes or quantitative data. It's a different story when we have categorical data, yeah, like apples, oranges. This was the example that we had last time. Their color is much better. Yeah? But of course, you can't use an infinite number of colors if you have many different categories. So that's a natural limitation. But we could also use area, so spatial region, and shape. Yeah? And we will have some examples later on. So the most effective, and I want you to remember this, that's why I repeat it all the time, is position. Yeah? So we use it in scatter plots, we use it in bar charts, we use length, which is almost as effective as position. And that's for quantitative and ordinal data. Then we have area, which is not that effective. I mentioned that a couple of times. And if we move from a pie chart to a donut chart, then we actually losing the angle and just need to interpret the area, which makes it harder for us. And the least effective, or among the least effective, is color for quantitative and ordinal data. Yeah? So what they've done here is they actually have continuous data values from 0 to 1.29. Yeah? And they added these colors. Yeah? And this is known to be not a good choice. Yeah? And I will explain in a minute why this is the case.
But do they have any other choice with a data set like that?
Yes. I will have great examples where we really compare the different choices. Okay, so talking about color, yeah, you may see this, it's a XKCD, so color names if you're a girl and color names if you're a guy, yeah, and that's what a lot of people think. So guys only know pink, orange, yellow, and a couple of colors, and girls have lots of different names. But actually, this guy who creates XKCD, he made a nice user study. Yeah, and he was able to show that this is not the case. Yeah, we almost have the same number or the same number of different names for colors. Yeah? So if someone brings this up again, you can say, no, this is not the case. Okay, now let's try to figure out why color is bad for quantitative data. So if we have continuous quantitative data, let's say from 0 to 100, and we want to encode it, then we need a color map. Yeah? So what's mapped to 0, what's mapped to 50, what's mapped to 100. And for this, we need people to order the colors. Yeah? Otherwise, it will not work. Yeah? So if you try to order these colors, it will be, I guess, quite hard. You might be able to order these. Yeah? I would agree that this is natural. So yellow, orange, and then red. But what about this blue and green? Yeah, isn't it red? On my screen it's red, but it's dark orange or whatever.
Gymnasium floor.
Okay, then we call it like this. Yeah, so if you try to order it, it's a really hard task, or it's almost impossible. Yeah, if you ask different people, they will have different opinions. Yeah, there is no unique order that we will perceive the same. But it's very different if we look at brightness. Yeah? If we try to order these, yeah, it will be very simple for us. We're really efficient at that. It will be dark to bright or white. Yeah? So if we assign white to 0 and black to 100, then we will be able to actually interpret the values in between. Yeah? And this also works if we pick one hue, like red here, and if we change the brightness. Then it's also very effective. but we shouldn't mix the color for quantitative data. So the channels that we have is brightness, saturation, and hue. Yeah? And if you implement something as a software engineer, then of course you can compose the colors using these three channels, yeah? Brightness, saturation, and hue. Brightness and saturation, they can be perceived as ordered. That means we can use it for encoding quantitative data. But with hue, we can't order it, as I said, so we can use it for nominal and categorical data, yeah? Because there we don't need to order apples, oranges, bananas. We just need to assign that this is an apple, this is a banana. Yeah? Yeah, I like this one because rainbow color maps, you see them all the time, and they're bad. Yeah? I just can say that they're bad. But it's not so easy to explain why they're bad, or many people don't know it. And this is I guess, one of the nicest examples that you have to demonstrate that rainbow colors are bad. So you have different kinds of rainbows, yeah, for land and for water. Yeah? And then try to interpret this. And yeah, I wish you luck with that. So why are rainbow color maps bad? As I said, it's hard to order. So this one would be much easier to order. And I'm sure you will agree. But there are other reasons. So if we look at this diagram here, it's just a projection of contrast and spatial frequency. Yeah? And if we just use brightness, then we can see even these effects here happening, yeah, where we have a low contrast and a high spatial frequency. Yeah? We see that there are some differences here. Here we can't see it at all. Yeah? So that's why color or rainbow colors are bad. And it creates artifacts. Yeah? And this is very bad because it actually distorts your data. So if we would use a continuous gradient from black to white, then it's a perfect mapping to our data, let's say 0 to 100. But if we have the rainbow color maps, and this is also a continuous mapping of the hue, yeah? Yes? No, that will be the same for all the color spaces. Yes, there it could be slightly better, but I will explain in a second why it's actually also the same there. Yeah? It will be the next slide, I guess. So here you see the effect that is happening, and there is this segmentation effect. Yeah? So we will see some objects that appear as objects, but they're actually not, because it's more continuous than it looks like in a rainbow color map. Yeah? So also here, this is much better than this one. So if you see doctors interpreting a CT image, then it's really good that they use this and not the rainbow color map. And the reason for this is that it's perceptually non-linear, yeah? Because we are interpolating the hue. Yeah? So we take the different colors, put them in a discrete manner here, and interpolate the hue. But if you look at the grayscale map, then you will see that the luminance, and that's the important thing, is constant. So the luminance change is constant. But here we have this peak in the luminance increase, which makes it for us, which gives this segmentation effect. And this is independent of the color scheme that you, of the color space that you have. So there is also, yeah, this example actually shows it really nice that there is this segmentation effect here going on. We will perceive this as an object and this is an object that belongs together, but actually it's really continuous here. Yeah? And yeah, yesterday on the media you've probably seen the size of the ozone hole. Yeah? And when you go to the NASA website, they use a rainbow color map, yeah, unfortunately. So you could write them an email and send them a link or so. Let's go back to this map example. Yeah? With this map example, I've shown that they're using different colors here. Yeah? And they're try to bring them in a natural order. yeah, which doesn't work. If you use just this here, then it will be more intuitive. I guess that's just an error here. No, that's what this shows here is the brightness of the different colors that you have here. Yeah? And this is not constant. So this is very dark, and then it gets bright again, and then it gets dark again. And this shows this incontinuous luminance projection that we have. Okay, so now let's move on from this bad color mapping to the good ones. Yeah? And they are the Brewer scales. So Cynthia Brewer, she did a lot of perceptual studies how to actually create color maps that are really effective. Yeah? And she created a website called Color Brewer, yeah? For the different data types where she just provides these different color maps, which are known to work well and to be easy to perceive, yeah? Or correctly to perceive. So if we have nominal data, then for instance, you can use the different hues, as we said. If we have ordinal data, then it's always better to just use grayscale or one hue and start with bright to dark. Yeah? This is the thing to do when you have quantitative data. And when you have a diverging scale, that means if you have data that is centered around 0, that means you have 0, then you should assign a neutral color to 0 and then use two different hues to left and right where you make them darker and darker. Yeah? And this will be the most intuitive thing to interpret. These are actually the different color scales that you will find, and this is also how they use it in Matplotlib. Yeah? So in Matplotlib, they're available, they're preloaded, and you just need to pick which color scale you want to have, and they have names, and these are the names that you find on Color Brewer. Yeah? So for diverging, there you always have this neutral color in the center. Then we have for sequential, which is for continuous quantitative data, and for qualitative data, so for nominal or ordered data, nominal data and or categorical data. Okay, when I go to the website, I will try to explain it here. So you say how many data classes you have, and I can say I want to have 7 different colors, and I want to pick sequential. So I have sequential quantitative data, and then you can just check out how it will look in this example. Yeah? You can also say I want to make it colorblind safe, then it will remove red and green. That would be diverging, so we have the neutral value in between. Here we can increase it to even more, so that we have the neutral color here and 5 different shades of orange to the left and 5 different shades to the right. Yeah, and you can switch to hex RGB and directly copy it into your code, yeah, if you want. But as I said, in Matplotlib, it's preloaded already. All right. So sequential Brewer scales. Yeah, if you want to see something like this, then don't do it, yeah, because you have these separation effects. And it's nonlinear, but these are much better. You will see that you have a higher density in the center, and this works, as I said, for grayscale and also for one hue. But you shouldn't mix, you shouldn't add a second hue to the other side of the spectrum. Okay, so this is a really good example, I guess. It's the internet from 2002, yeah, and they're making a huge mistake. What would be the mistake? Any ideas? Yeah? The background? Yeah, you could say that the contrast is not that good, yeah? Yes, but actually what they have here is categorical data. Yeah? So what happens here, you have these 4 shades of different green, which you would naturally start to sort. Yeah? But actually they have just oranges, bananas, and apples, let's say it like this. I guess it's different types of servers and machines. Yeah? And here they have 22 colors. Yeah? And this is way too much. We will not be able to actually look at this point and tell if it's this, or this shade of green. Yeah? That's just impossible. So the rule is, if you have nominal data, then do not use more than 6 to 10 colors, yeah? Because we will just not be able to interpret the legend, yeah? And to make the association. If you have more than these categories, then you have a problem, because you should not use color. Yeah? You should try to reduce your categories probably. Okay, yeah. Now I'm wrapping up color by introducing color blindness. So 8% of males and 1% of females only are colorblind. So in that case, actually, gender moves from a nominal data type to an ordered data type, yeah, because females are better than males in that case. Yeah, most common is red-green weakness. So this would be the actual color that is projected on your monitor, for instance, or on this projection wall. And this is how people see it if you're colorblind. And there are two different kinds of color blindness that they introduce in this paper. Yeah, and you all know these tests here. You can do them on your own. So what would this be? 26, yes. 7, yes. That's a bit hard. I guess it's 74, yes. So who of you know that they're colorblind? It's nothing to be embarrassed about, yeah. So it's also okay if you don't raise your hand, I guess. Okay. But in a large crowd like this, of course, there are some people that are colorblind. And when you design your visualizations, you should always use or try to use color maps that are colorblind safe. Yeah? And that's possible. I mean, also in Color Brewer, you can just pick this option and you will get colorblind safe maps. So that's the last slide for color that I have. Color is relative. That's also perceptually interesting because it depends on the context. Yeah? And you've probably seen these examples here where we use the same color. Yeah? So this is actually the same color here. And these are also the same color. Yeah? But depending on the surrounding, they look different. On my screen, this is much darker. Yeah? It's also here that this appears to be lighter than this one. But actually, they're the same. Yeah? So if you project something or if you create a heat map, then you will have this effect and you can't actually solve it. Yeah? But it's good to be aware of the fact that that this is going on, that the surrounding influences your interpretation of the color or your perception of the color. So these are all reasons why colors are overused usually, and you really should have good reasons for that you want to use color in your plots or visualizations. Okay, the last part of my talk today will be about design principles. And again, we have these non-effective examples. Yeah? And there was a discussion going on. So for instance, Andrew Gelman from Columbia University, he said perhaps every scientific journal could have a graphics editor whose job is to point out really horrible problems and require authors to make improvements. That's his suggestion. He said, I'm not angry at the authors for publishing bad graphs. Scientists typically don't get training in how to construct or evaluate graphical displays. And that's of course true. You can't really blame them. Indeed, I've seen stuff just as bad in JASA and other top statistics journals. But it would be good to catch this stuff before it gets out for public consumption. Yeah? So adding editors to the journals would be one way to actually address this problem. Another way would be to educate scientists, yeah, and also people in industry. And Nature Methods really did a great job. They tried to, or the editor-in-chief, Dan Evanko, he established 2 columns in the journal, yeah? Points of view and points of significance. points of significance is actually written by statisticians, yeah? And they tell you what you should think of when you use statistics as a biologist, for instance. And points of view, it's written by Ben Wang from here in Boston, from, how's it called, the Bioinformatics Institute? The Broad, yeah. And Niels Gellenberg from Harvard Medical School. And they always invite other authors, and they together write the points of view column. In terms of, so it's good to educate people, but there are, of course, this is not new what these people are telling you in their columns, and it's also not new what I'm telling you, of course. So there are some really good books, like Edward Tufte's book. Tufte is really popular in our community. He wrote this groundbreaking book, The Visual Display of Quantitative Information. Yeah, if you buy a book by Tufte, then you should first go for this one. And I will just introduce some principles that he talked about in his books. The first one is scale distortions. Yeah? This was on Fox, and they compare if Bush tax cuts expire, yeah? Now and in January 1st, what would happen? Yeah? And actually, if you change the scale, then it wouldn't be that horrible. Yeah? And this is lying using visualization, yeah? Because people, of course, they know that the effect is not that large, but they do this on purpose, yeah? And you shouldn't do that. The same happened here, yeah, and this is really funny, not because it's 3D. This is we discussed that already, but they actually tried to show this trend. But what they did is they shuffled around the years, yeah. So you have 1921, 1999, 1934, 2006, 1998. So it looks like a trend, yeah. And in 2012, it was really horrible, yeah. So this is one mistake here, and the second one is that the scale starts at 53, yeah, and not at 0. If you would properly plot it, then it wouldn't be that bad. Of course, it's a problem. Yeah, I agree. Another example is this. So this is from CS 171 of the visualization course that Hans-Peter Pfister is teaching, and they tried to find out if there is a difference in the grading when you compare the different TFs. Yeah? And if you plot it like this, you will think, oh boy, there is really a big difference. I should go to this TF and not to the other one. Yeah? But if you look at the actual data and you plot it in a correct way, then it's kind of okay. Yeah? There will be some differences. Of course, they're human. Yeah? But it's not that bad. So the message here is always start your bar graph at 0. And also for your homeworks, it's really important. So, and if you don't start it at 0, then clearly mark it. Yeah, but the rule is you should start at 0. And another important thing for the homework is that you need to label the axis and also show the units. Yeah. Which is, of course, important if you have temperature. It makes a difference if it's degree Fahrenheit or degree Celsius. Yeah? So make sure to label them. That's another thing that happens quite often is using two different scales for the same axis. Yeah? If you look on the left side, you see 0 to 60,000. And on the right side, you see 47,000 to 54,000. Yeah? And I mean, you immediately start to compare these two curves, yeah, and to interpret the relation between them. But if you plot it on the same scale, and you shouldn't mix scales in one graph, then it would look really different. Yeah? So don't do that. But this is probably, this rule is not as hard for line charts as it is for bar charts. Okay, so global warming. Some people think that global warming is not a problem. Yeah? And if you look at this data, you could say, well, it's going up and down, and it's not a problem. Yeah? If we put it in context, yeah, then you will see, if we just show this part, and this is the regression line, then yeah, it's still not a problem. But if we add more historical data, we will see there is a clear trend. Yeah? Although the values are not constant because it's hard to measure that, of course, but there is a clear trend. Yeah? Global warming is happening. Yeah? Yeah, you just need to accept that, I guess. But of course, you can lie using visualization. Yeah? That's another good example, lying with scales. It's from a textbook, and I took it. There you have a scatter plot, and they just change the scales. Yeah? And I guess depending on the story that you want to tell, you can just pick the different scales. Yeah? If your story is that your data is all the same, then pick this scale. Yeah? If your story is that it's all the same in X direction, but you have this spread in Y direction, then pick this scale. Or if you would say, it's very different. Yeah? There's a increase here, or there's a cluster, but it's quite scattered. Yeah? And this just is a choice of picking the scale. Yeah? And in Matplotlib, you can always, so there is a default, it will try to fit your data, but you can also say enforce from 0 to 100. Yeah? And this is also important for your homework to think about the scales. Yeah? And scales can be used to lie. Okay, so scales are critical. So what are your bounds? What are the upper and lower limits? What scale work? You need to always think about, should I use a linear scale, a log scale? Should I clip the data? Yeah? If you have some outliers, which are errors in the data, then just clip them to bring the chart back to the right range. Do you want to use relative or absolute values? And scales can also be used to make it comparable. If you have two charts and you use the same scales, they are comparable. If you use different scales, you will have a very hard time to compare them. Okay, another principle by Tufte is the lie factor. Yeah? And the lie factor is the size of effect shown in a graphic divided by the size of the effect in the data. Yeah? And this demonstrates that area, it actually distorts your perception. Yeah? So area, as I said, is not a really good, is not a really effective visual attribute. And this was also a good example. So we have Steve Jobs, who is known to be a really good presenter, and he presented the smartphone share. Yeah? And this was in, I don't know, 2008 or so. And the Apple share was 19.5%. Yeah? But it looked, so the impression was Apple is doing really good. Yeah? And they made some design choices that made that happen. For instance, they used a slightly tilted 3D version, and they put it as the centerpiece. Yeah? So it's the most salient. And they also used this bright green, which is a very positive color. Yeah? And even if this share is bigger, yeah, this one appears to be bigger because it's tilted. Yeah? And this is, people think about that a lot. Yeah? When they create really important visualizations, then they try to influence you. Yeah? But you need to be aware of that. Okay, if we just remove the third dimension, yeah, then it will be more honest already. And the best way would be, or the most effective way, but it's not that fancy, to show at the Apple keynote, I guess, is to just show it as a bar chart. And there we clearly see other is more than Apple, actually, at that time. That probably changed, of course. Yeah, that changed for sure, because RIM is not at 39% for sure. Okay, yeah, this is from Yale Daily News. And so this also happens. Yeah, it seems to be obvious that a pie chart should sum up to 100%, yeah, because we're talking about composition. Yeah, a pie chart should always be one whole. Yeah, and you have the different slices; they should sum up to 100%, which is clearly not happening here. Okay, now the explanation why 3D is bad, and I will do this using pie charts. So this is kind of a meta joke, yeah, blue pixels and red pixels, and the share is actually smaller. Yeah, I think you get it. So what are we trying to do? Is the rule by Tufte is you should maximize the data inc ratio. Yeah, and this is what Raphael said, that his toner is used up quite really fast when he prints. So what you should do is the data inc, so the ink that you use to encode your data divided by the total ink used in the graphic. Yeah? And this is a number that you want to maximize. Yeah? You should not use ink for example, this shadow here. You shouldn't use ink for this top bar here. So this ink is not encoding data. Yeah? That's just because of the 3D effect that you want to have. Yeah? And this is called data inc ratio. It's a very interesting concept. If you make it better, then just remove the third dimension and you will, what's happening in the background is of course that this data inc ratio is going up, which is a good thing. Yeah, I said this a couple of times, but now an example. Yeah? It's a three-dimensional bar chart. Yeah? And these examples are from this Nature Methods points of view column. Yeah? And I have lots of, I put a lot of examples in my slides, and I always put the reference there. So they actually try to make the point that 3D is bad. So what's happening is you have bars that occlude other bars. And as I said, you would actually need to rotate this to make the bars in the background be visible. And of course, you can't do that with a figure in the paper. So this is bad. And also there is a difference in the appearance of the relative height. Because it's a perspective distortion, like in real world. If things are far away from us, they appear smaller. And this is also what's happening here. So bars that are here at the back, they will be smaller. But this is not because the data is that the number is lower, but this is just because of the distortion that you have because of the 3D effect. So which one would be the tallest bar? Yeah, that's a very simple test to actually demonstrate that this is not working at all. Which one would be the tallest bar? It's very hard to tell. But the other question is even more interesting. What is the pattern in the data? Who sees a pattern there without looking at my slides if you have them already? Yeah, it's not a sinus, but it's similar. What's this? Other guesses? Yeah, this is the pattern. It's a question mark. And this is very nice to show this using a question mark, I guess, because people will not see the pattern, although it's a very simple pattern. Yeah? If you use a 2D heat map, just using grayscales, it will be immediately visible. Yeah? And the data inc ratio is also going up. Okay, and yeah, what is going on here is the perspective distortion that I mentioned. So if you encode your data using position, and this is clearly happening in a bar chart, yeah, position has a meaning. But if you add this third dimension, then the position will be changed, but not because of the data, just because of the projection. And also the size will be changed because of the projection and not because of your data. Okay, but there is an exception. We can use 3D if you actually show a 3D phenomenon. Yeah? And there we can use this natural depth cues that our brain is able to interpret to perceive 2D images as 3D. Yeah? We can, for instance, use partial occlusion. Yeah? If an object is behind another object, it will hide this one, and we will immediately see that this is further away. Then we have a difference in size, and we will be able to actually see that because it's what's happening in real world. And we have a difference in the shading, yeah? Because you have a light source at some point, and then you have shades in your representation. Yeah? So if you have a real 3D data set, like this protein structure here, then, or it's this DNA structure, then you will actually then it actually makes sense to use 3D. Okay, so I guess the last rule that I want to present, Tufte's last rule, is avoid chart chunk. Yeah? So try to remove these visual elements that distract from the message. Yeah? And this looks quite clear. It's a bar chart, yeah, but you can improve it a lot. Yeah? First, we start removing the grid lines. Yeah? If it's only about the overall trend, this is valid. If it's really about tiny differences, then grid lines are important. But in that case, we remove it. Then we remove the background. Yeah? There's no point in adding a color here. Then we remove the border here. Yeah? Then we introduce these tiny white parts to actually don't need to use grid lines, but we see these ticks here. Then we remove the ticks because they're already contained in the bars, and that's the final result. Yeah? And if we look at this matplotlib example, and you can go to this URL to see the code, then this would be where we start, and then we remove all the stuff, and that would be the final result, which removes this chart chunk. Yeah? And it saves toner. Okay, so Tufte's design principles summarized are you should go for clear, detailed, and thorough labeling and appropriate scales. Yeah? And we've discussed several examples. Then you should think of the lie factor. So the size of the effect should be directly proportional to the quantities that you have. Then we should maximize the data ink ratio, yeah? And we should avoid chart chunk. That are really simple design rules, but if you follow them, you will make the world, I guess, a bit better. Okay, so the last 2 or 3 minutes, I guess, some visualization critique. So I present this, and this is from Cole Nussbaumer from his blog, and it's called Death to Pie Charts. And he's really religious about pie charts, so the blog posting starts with, I hate pie charts. I mean, really hate them. And then he tries to improve it. And the first thing to improve it would be to remove the color, because you have way too many categories to actually have some meaning for it. Yeah? You just introduce this white spacing here, and that's enough. If you have the labels in place, that's okay. But even better would be to move to this bar chart. Yeah? And that's the final step that would be most appropriate. Another example, and that's the last one that I have, it's Harvard troubles. Yeah? So what's wrong with this chart? First I tell you what the data of the chart is. So in 2008, they had this problem that the revenues from the endowment funds was radically going down. Yeah? And in that report, they actually tried to figure out what would be the influence, or what's the influence on the different schools. Yeah? And what you see here is the total endowment that they get, so percentage of the total endowment. Like this would be 40%, and here you see the share of operating revenues from endowment income distribution. So how much of this revenue they use to actually cover their operating costs. Yeah? So what's wrong with this figure? Yes? Yes, so it mixes, is that what you mean? It mixes a column bar chart and the row bar chart. Yes, so that obviously makes it harder for us to compare it. If we would just stack it on top of each other and use bar charts, it would be much more intuitive. What else? Design principles. Yes? Yes, that's what I've mentioned. Is that so that you just need to rotate the first one? Yes?
Like too much ink that's not like data ink?
Yes. What would be the ink that you don't need?
The whole background situation.
Yes. What else? Yeah, there's lots of ink that you don't need. The colors. I mean, the colors, they match, so that's okay, but it's not it's not perfect, I agree. They're too dark, so you can't read the labels here. Yeah? And there's even a difference that this other bar is completely missing in the second one. Yeah? So that's also bad. So if we want to improve it, what could we do? I mean, we could remove this chart chunk, and as we said, we rotate one of them, and then we would have this. Yeah? And this is the first redesign. So what you have here is, so Radcliffe, it uses 80% of their revenues for covering the operating costs. Yeah? So one could think, well, they will really have a problem if that happens. Yeah? But there's a better way to actually show this. And because here we are interested in the correlation. So how does this value relates to this value? So we could make it a scatter plot, right? Yeah? So we have the percent of endowment funds here and the percent of operating fund sourced from endowment here. Yeah? And then we see Radcliffe, it's actually, it has a really low number. It doesn't get much endowment. And here you have a really high number here. So it uses a lot of the costs to cover the operating costs. And that would be probably even better to actually show it as a share. Yeah? Because here we see the biggest problem would be for arts and sciences, because they have the biggest number. Yeah? For them, if the revenue from the endowment goes down, they will have a big gap in their budget. Yeah? And for Radcliffe, actually, it's not that much money. Yeah? So for Harvard, as an institution, these schools would be much more influenced by the revenues, by this decrease in revenues. Okay, so further reading before Raphael takes over. It's Edward Tufte's books. I can highly recommend them if you're interested in InfoVis. Then Stephen Few, so he's also really big in charts, so basic statistical charts and business informatics. And he wrote a great book, Show Me the Numbers, and also the other ones are really useful. This is about basic charts. Yeah? And the last one is Tamara Mansner. Yeah? And I've used some of the examples are from her book. It's called Visualization Analysis and Design. And I can also recommend this one. Okay, so next Tuesday we're going to talk about what to do if we have lots more dimensions. And Raphael is going to talk about distance and clustering, and then about dimensionality reduction. So how you can reduce the number of dimensions to actually have something that you can easier visualize. Okay, that's from my side. Are there any questions before I give the mic to Raphael? Okay then, thanks for listening and see you on Monday.
Okay, so very quickly, I don't know if we're going to get through everything today, but we're going to discuss some of the concepts and data that we're using in the homework. Thanks. So one thing I want to mention about the visualization topic is that an important distinction to make when you're working on homeworks and such is that there's things you do for yourself to discover patterns and just to explore the data, and then there's things you do when you present it. So a lot of what Mark has been talking about today are some of the stuff is important for discovery itself, like the use of the correct colors and scales. But then in terms of presentation versus exploration, you want to be fast as well when you're exploring. You don't want to spend a whole lot of time making a picture look very, very beautiful when all you're doing is trying to follow clues. So that's an important thing to keep in mind. It's a balance that we have to keep when we become data scientists. So I'm saying that because you're going to see some pretty ugly plots here. All right. So the first, this is related to the homework, and I want to explain this quickly because you need it for the homework, and I didn't go over it completely the first time. So the normal distribution, I showed that equation previously. Here's a version with numbers stuck in to the locations you want. So this is, if you want to find out, for example, how many people are more than 6'4", males that are 6'4", we know the mean is 70 and the standard deviation is 3. That formula I gave you answers that question. That's the formula with the numbers put in the right places. You have the mean is 70, SD is 3, and you want to know from 76 to infinity. Okay, so then you solve that equation, and you solve that integral, and you have the answer. Now, solving that integral, you can try, but you won't. It'll be quite difficult. You don't really have to worry about that because it's in Python, it's in MATLAB, R, SAS, any package you use, any software you use will have a function that gives you this. And I'm going to tell you a little bit more about that. Go ahead.
Would the infinity sign be negative?
Oh, no, it's positive. Thanks. Yeah. All right. So here's, now I have it upside down again. So just to be consistent. So all you really have to memorize, this is a nice thing about the normal distribution, like that equation looks kind of ugly, but it's actually not something you have to memorize. Because all you really need to know is one case when the mean is 0 and the standard deviation is 1. And then the formula is a little bit easier to remember, but you don't even have to remember that because there's a function in your computer that gives it to you. And I always think of phi because that's how I learned it when I learned it. But these days, I just know the command I type on the computer that gives me phi of z. Right? So there's a command that will give you that. So to answer the question, how many people are more than 6'4", you first convert that into standard units, which we talked about. So you subtract the mean. That makes your list have no mean 0. You divide by the standard deviation, and now your list has standard deviation 1, and you can use that formula. So you convert it, and you realize that a male who's 6'4" is 2 standard deviations away from the mean, and then you can just find out what proportion of z's are bigger than 2. So phi 2 gives you how many are smaller than 2, and 1 minus that gives you how much they're bigger than 2. So basically, the message is you just have to find out what phi is on your program you're using, and then you can answer all these questions. You don't have to actually keep track of the mean and standard deviations. You convert to standard units, and then it becomes easy. Okay? So for one of the homeworks problem, all you'll need is that one function to answer it. Okay? All right. I'll let you figure out what the function is in Python. All right. So now to the baseball data sets. So we're going to be using baseball a couple of more times. So if you are not familiar with the game, maybe read up a little bit on it. It's a perfect time to start following the Red Sox. And then you'll get jokes like that when I tell them. So we're going to be using this database that you can link. It's linked there. And this is going to give you a zip file with a bunch of tables inside. So one of the things you'll learn in Python is to be able to very quickly, there's a function that we tell you about, or maybe we tell you enough to find it, so that you can go and see what's in it and grab any one of those tables really quickly. So let's suppose you're a real data scientist and I just ask you this question without giving you hints. How would you come to this? That's kind of a hard question to figure out, and it really comes down to experience and knowing how to search in Google and just being knowledgeable about all the stuff that's out there. But once you get to this, then we still have to go and find out what are the tables that we need. We need to have for each team, for each year, how many games they won, and we need to know how much the salaries were. So once we read there's a in the next slide there's a website that gives you everything that's in each one of these tables. You could look through and figure out, although we already tell you this, that what you need is the what's the name there, teams and the salaries tables. That's all you need. So you can see them down there. So once you can load up the teams table. You load it up to Python, and the first thing you're going to see is it has a lot of columns. So those are the columns that I'm listing them out. There's a command in Python that shows you that. And what do we need from here? All right, so we need the wins, W, and we need the, what else? the year and the team. I think that's it. And if you're going to get technical, you want the losses too, because in 1994 there was a shortened season. So you don't have to do that for the homework, but if you really want to do it right, that season wins they're going to be less wins because they're playing less games. All right, oops, I went too far. All right, so here's the teams table. After I take out everything I don't need, it goes way back to 1871, and it has 2,745 rows. So every row is a team for a year. Okay. Now we're missing, to finish this off, we need the salary to get to the homework. And here's where it gets a little complicated, and why it's not just straight statistics, and it becomes more data science because we have to do a little bit of wrangling. So how do we get the salaries? There's a salaries table. Here it is, ordered by salary, but it's not by team. You see that? Anybody know who Rodrial 01 is? A-Rod. A-Rod is a player who has the top, 6 salaries. That's $33 million a year that he got paid in 2009 for not much. Actually, that year that year he was maybe worth it, but not 2012, that's for sure. So, and then there's Vernon Wells, who is definitely a waste of money. And then, this guy, you know who this guy is? Smani. He used to play in Boston when he was good. All right, so there you have it. So those are all the players. There's 23,000 of them, and it's per year. So if we want to get the teams, what do you have to do? If you want to get the team salary, now you have to do a little bit of programming. Okay, everybody see that? This doesn't have it for the teams. So there's this concept that we use often in data science. It has many names. This is one of the names that is given to it by Hadley Wickham. Split, apply, combine. This is kind of a general idea. So how does it apply here? We're going to split this data into teams. So we have a bunch of tables. And what else? And by year, right? Team year. So every team year has a table. And then we're going to do something to that table. We're going to apply something. We're going to basically sum up the salary column. And then we're going to combine them back into one table, and that's what I'm showing you here. So these are the teams, the teams with the highest salaries in history. You can see that one particular team shows up more than others. And the second one, there's the Dodgers of last year. That's 231 million, if you're not want to count the digits. Okay? So now we can make a picture like this. There's the year and the salary. Now we have the information we need. Okay? So once you have that, then there's one more step you have to follow. So we have that table and this table, and now we've got to put them together. And we can't. It's not as straightforward as just putting them next to each other because they're not in the same order. We don't have salaries for every year. Right? We only have them for recent years. So that's another thing you have to learn to do. You got to put these two together. And once you put them together, then you have what you need. It should look something like this. Okay? So now you can make a picture like the one we talked, like what you want to do to start looking to see if it's an outlier. And there's a pop-out principle that Mark talked about. I'm using color to show Oakland. I use green because that's their color, not because it's the best one to use. All right, so that's the plot. You want to be making plots like this and look at them and try to answer the question. There's one quick thing I want to get through the whole thing, so I'm going to go pretty fast. But there's one other thing that I want to mention here. You don't have to use it for your homework, but it's kind of a nice thing to start thinking about because we're going to use it later. By adding a regression line, there's something that it's related to a visualization principle. What we're really interested in this picture is not how high you are, because how high you are doesn't say anything about how much you're winning when you're spending less. What you really want to know is how much you're winning compared to what you're expected to win when you're spending this amount of money, right? So the Red Sox, who won, well, the Yankees won as many as Oakland, aren't going to be as impressive, even though in this picture they're just as high. They're actually, I think, one higher. So what we can do instead is plot the distance to that line. Think of the line as what you expect to win, and we'll say more about why that is, why the regression line does that. We said a little bit about it previously. And then the picture looks like this, and now it kind of really pops out. See the difference? So now the Yankees don't look nearly as impressive. Okay? That's not, again, this is optional for the homework, but it's just something we want to be talking about. We'll be talking about later. Okay. Now, in the last 2 minutes, just a little bit about the income data. You have, again, 2 tables. The first one is just a table that attaches the continent to the country. One thing you'll learn here is that if you go to the actual page and you try to grab that CSV file from the web, it won't work. And it's because it's not really a CSV file. It's a web page. So when you try to read it in as a CSV file, you'll get a mistake because Python is going to expect Python's going to get back HTML back. So there's some tricks to get around that, to read in HTML instead of CSV. And again, that's something that we give you some hints on how to get to. So here's then the other data set that has year and the country and then the income. This is income per person. So now we can make a picture like this. Okay, so you'll see that you make a histogram, for example, and you can see in 1923, this is what the histogram of countries. So every point that's used in this picture is a country, not a person. So you can you already see that there's some rich countries and then there's a lot of poor countries. And related to some of the Mark talked about, the scale, we can actually also look at the log scale. And what that does in this case is it lets us see a little bit more what's going on at the bottom. Instead of seeing, oh, there's all these poor countries, there's a little bit more going on down there where you even have countries that make almost 10 times as more, but they're all grouped, in that previous picture, they're kind of all grouped at the end. So it gives you a little bit of a different perspective. There seems to be more, the world seems to be more complicated than just the poor countries. So then the next thing you're going to have to do is attach a continent to each country. And one of the things that you should not get frustrated by is that not all countries, and I put them in quotes, have a continent, because one of the tables doesn't have all the countries. And the reason is, you can see it from here. These aren't really countries. I'm just kidding. Actually, Puerto Rico's there. That's where I'm from, so I shouldn't make too much fun. But you can see that some of them aren't countries anymore. East Germany. There's another one. There's like West Germany, and there's some other that have disappeared. And others are like tiny little islands or colonies. And you also have problems like USSR is there if you keep going down. But then there's some that shouldn't be there, and that's something that you'll have to figure out if you have to fix it. Maybe they used a different name for the same country. New Jersey is also there. Okay, so these are things that you'll have to take. You might have to do a little bit of extra work to get them all like you want. So we're going to compare continents. There's the medians for each one, and the IQR. Mark talked about this last time. Again, we're using the split, summarize, join. We split by continent, take the median, IQR, and then join it back into a table. But this is not, we really want to be seeing, this isn't really very informative because we suspect there's more going on here than just changes in mean, and here's a box plot. So now the concept is split, make a box plot, and then join them in the same picture. So in Mark's lecture, he was saying if we put each box plot separately, it's going to be very hard to see that for example, Europe is higher than Africa. If Africa had its own plot, then the scale would go to only up to like 2,000 and some, and it'll look kind of like the same box plot, and you actually have to go to the y-axis to see that it's not the same range. So putting them all with the same axis really makes you see what's going on. So some of the things that we see here is that there's outliers all over the place. Like here in North America, you want to guess what that one up there is? Yeah, that's the USA. How about those two? Yeah. And then nobody's going to get what this one is. It's Cuba, I think. This is 1923. So you can also, so another thing that is nice to do with box plot is to add points so you can see a little bit more. These now actually have the names. Oh, here's Cuba. And Argentina is richer than Sweden. Anyways, you start seeing things that might be interesting. I don't know. You don't need that for the homework, but this now starts showing really that there's clearly some rich countries and then some poor countries down here. And what the homework is about is to try to see how if that has been getting worse in terms of separation, better, or has stayed the same for countries, not individual peoples. Okay? So that's it, I think. If you have any questions, I'll stay a little bit longer.